here I have a situation in which we have an amplifier input port with the equivalent input NOR sources modeled. So for the rest, I have nothing of the amplifier, and I told you at this stage it is not of interest. And I have a source. In this case, I have a signal source in the form of a current source with a parallel impedance, usually we call it the source admittance, and noise associated with this source admittance. And for some reason, I decide to put some impedance in series and some admittance in parallel with the signal path. The reason I can tell you, the reason is that I want to show you that you shouldn't do it. So first I do it, then I will show you what happens. And then we say, we have a very good design. Conclusion at the end, we say, don't place impedances in series or in parallel with the signal path. Of course, we do it regularly, but this is going to be a very important rule that we are going to use throughout the course. So I put ZSE as in series and associated, because it has, let's say, assume it has a real part, associated with it, there is a noise source, a noise voltage. And as soon as it is in parallel, I don't model noise voltage, but I model noise current. I could have done voltage as well, of course, but it's more convenient. That's what I know from practice, to do if something is in parallel, to model with current. So here you have a parallel admittance and also associated noise modeled by this IP. Now let's see what is the impact of this on the signal to noise ratio of the source. So the source itself had a signal IS, a noise INS, and now I want to know at the end the total noise as if it came from the source. So I want to have an equivalent model in which I say all these contributions now, all the contributions of VSE and VN and IP and IN, I want to have them represented by something at the location of the source. And then I call it the total source referred noise. And of course, this total source referred noise will be larger than the noise that was only associated with the source, which is INS. And then we can say something about a noise figure. First thing is I shift Vn through the node of IP and YP. You see, I shifted through this node. So it is now in all branches. We have 1, 2, 3 branches. This was basically one node, and I remove it here. The next step is add this one, the Vn to VSE. They're just simply in parallel. And I'm going to convert Vn, the contribution of Vn, into something in a current in parallel with IN. So how does it work? Look, Vn is now added by VSE. Here, this Vn, and now you see the importance of the plus and minus sign. They came all from one source. So they are correlated. These three with the cross are correlated. So this plus now has a meaning. The plus Vn plus VSE has a meaning. And here we have Vn in series with the current source. Well, a voltage source in series with the current source cannot change the current of the current source because the impedance is infinite. So this Vn in series with Yp can be omitted. But this one, I can make an equivalent Norton model from this, and then I can add this one to what was already there, which was In. So I have then In plus Vn times Yp at the input of the amplifier as a current. So we can leave this out. And the next step is that I'm going to add these two current sources. That's a little bit more simple. So I just put it in there. So you see, I have now eliminated the two equivalent input sources, and I'm shifting in the direction of the source. So here, this one, I can split, I can redirect it over here, INS, and over ZSE. And that's what I'm doing. So you see the term adding here in INS, and you see an extra contribution here, IN plus VN YP plus IP times ZSE. And you understand already my next step, it will be converting this one into a voltage that I can add to this one. So you see, it is like I'm going now from Norton to Stevenage, and I have it like here. And now I end up, this current source is at the correct location. This is already in parallel with the signal source. So the INS plus IN plus VNYP plus IP is already at the good place. But the voltage source next to ZSE is not at the right place, and I can convert it into a current. Just swap if you don't see it immediately, because you can swap it, it doesn't change the network. And now you see that this one, this voltage source that is now there, can just be converted together with YS into a current in parallel with INS. So that's what I'm doing. And we have everything together here. And now you see what I'm doing. I'm collecting the terms of the original noise sources because they were correlated, and I can just add them. You see, and then I can write the spectral density, and I have to square all these terms. And here you see in gray, you see the original situation, and here you see the total result. Now let's look at the total result. I'm not so much interested in the deriving of this formula. You can see it in the book. It is done step by step. I'm more interested in what does it mean. Let's look at it. We have the total spectral density of the total current noise is of course more than that was originally there, that was SINS. That is just associated with the source. And you see all the other terms are contributions from other noise sources. And you see 4 noise sources. VSE, that was the noise associated with this impedance that I inserted in series with the signal path. S of IN was the equivalent input noise or current noise of the amplifier, the 2-port. SVN was the equivalent voltage noise of the amplifier, and SIP was the noise associated with the parallel admittance that I placed in the signal path. Now, even so, if these impedances were and admittance were noise-free, for example, ZSE is a capacitor and YP is a capacitor, or they are inductors, or they are combinations of inductors or capacitor, then they are noise-free. But you still see that then there is an enlarged contribution of SIN because the product of ZSE and YS is not 0. And here also, you see, in SVN is also increased. So even if the impedances are noise-free, and that is very important to realize. So even if we connect our microphone to the amplifier with a capacitor, and the capacitor doesn't generate noise, it can affect the signal-to-noise ratio. And here you see how it does, how it affects the signal-to-noise ratio. So design conclusions. Insertion of impedances in series or in parallel with the signal path should be avoided. Generally, they increase the influence of existing noise sources. That's what we have seen from these expressions, from our work. If these impedances have a non-zero real part, they also contribute noise themselves. So then they are noisy and they add noise. That is quite logical, but that is not the only contribution we have. Only in narrowband applications, they may improve the noise performance. And I want to give you a little bit of an example. Let's say we have here an amplifier and we have a source with an inductive character. And now I'm placing a capacitor in series with a signal path. So the capacitor itself is noise-free, and hopefully you know about series resonance. So at the series resonance frequency of this combination, there's suddenly no impedance in series with the signal path because it's 0. Which means that there is a frequency at which IN does not contribute more because of this LS that was originally in the left figure. IN times the impedance caused by LS was giving you noise voltage. But now IN, the contribution of LS is cancelled by a voltage across CC. But this is only in narrowband situations, and you can see it from this example. It is only when omega is in the vicinity of the resonance frequency of the network.